So today we're going to be talking about section 3.1, which is basic concepts of probability and counting. So some of these things should be things that we've talked about before or you've seen in other classes, but we're going to talk about a few things today. So the first thing is, it says a probability experiment is an action trial which specific results are obtained. The result of a single trial is called an outcome, and the set of all possible outcomes is called a sample space. An event is a subset of the sample space, and it may consist of one or more outcomes. So, for example, if we are to flip a coin, right? And I'm not going to draw a face on it, right? Okay. There's somebody's. That's a coin right there, right? Heads, or the back would be tails, right? Heads or tails. And so flipping a coin is has two different outcomes. It either has heads or tails. Those are called outcomes, right? And our sample space is the set of all possible outcomes. So if you're going to do one flip, okay, your sample space is going to be either heads or tails. Now what changes is if I'm going to do two flips, right? Two flips. And so that would be, I could do heads, 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 tails, tails, heads, or tails, tails, right? So now I have four different outcomes, right? An event would be, let's say I'm going to flip, this would be considered our event, which would be one flip, two flip, whatever. Okay, so it's a subset of the sample space. All right, and it can contain one or more outcomes. So let's look at an example. Example 1, it says, a probability experiment consists of tossing a coin, then rolling a six-sided die. Determine the number of outcomes and identify the sample space. Okay, so for our coin, we can either have heads or tails, right? And for our die, okay, we can have 1, 2, 3, 4, 5, or 6, right? And so now we can list out all the possible outcomes, okay? And so I'm going to get rid of some of this right here so I can write that down. All right, so let's list out all of our possible outcomes, okay? So we could, all right, we could either have a heads and a 1, or a heads and a 2, or a heads and a 3, or a heads and a 4, or a heads and a 5, or a heads and a 6. Or we could have all of those as tails. Okay? And I'll just do ... because you know that means we could have all of those. So, so the sample space then would be all of those. And so since we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, there'd be 12 outcomes. Okay, 12 different outcomes and 12 outcomes in our sample space, right? Okay. So here's one that you can go ahead and try on your own. Now, we can have something called a simple event. Okay, it's an event that consists of a single outcome. In example 1, tossing a heads and rolling a 3 is a simple outcome, meaning if we had heads and 3, that was one of our 12 outcomes, but if that was the only one, that would be a simple outcome, right? Where something is not a simple outcome is when you can say tossing a heads and rolling an even number. You'll see I have three different outcomes, three different events, right? And so it says, determine the number of outcomes in example 2, and then decide whether it's simple or not, and explain your reasoning. Okay, so let's look at 1. For quality control, you randomly select a machine part from a batch that has been manufactured that day. Event A is selecting a specific defective machine. So, a specific defective machine part, right? And so that would be one part, right? One part. And so this one is going to be considered simple, right? Part B, it says you roll a six-sided die. Event B is rolling at least a 4. Okay, well, 4 is at least a 4. 5 is at least a 4. And 6 is at least a 4. So that's 3 events. So this is not simple, right? Okay, so we can see the difference. So I'd like you to try the next problem on your own. Now, how we can figure out the number of events happening in it is something called the fundamental counting principle. And it says that if one event occurs m ways and a second occurs n ways, then the number of ways the two events can occur is m times n, right? So if we are, I take our coin, right? There's two outcomes, right? From flipping a coin, heads or tails, or the die, there are 6 outcomes, right? And so if we wanted to figure out how many total there are, we would take 2 times 6, which is 12 outcomes, and that's what we got in example 1, was that there's 12 different outcomes. And so there they are. All right, example 3. It says that you are purchasing a new car. The possible manufacturer, car size, and colors are listed. Okay, so how many manufacturers are there? Well, there's Ford, GM, or Honda. So there are 3, right? Then car size, you could do compact or midsize. So there's 2. And then finally for color, there's 1, 2, 3, 4 different colors, right? So how many different you could do? It asks you to draw them as a tree diagram. So we're going to do that. We're going to say Ford, GM, or Honda. Okay. Then from each one of those, I can pick 2 types, compact or midsize, compact or midsize, compact or midsize. And then from there, we can have 4 different colors. 1, 2, 3, 4. And so I'd say white, red, blue, or black, or green. 1, 2, 3, 4 down here. And then I'm just going to draw the leaves out. I'm not going to label everyone. You can in your notes if you'd like. 1, 2, 3. Okay, so if we count every leaf, there's 4, 8, 12, 16, 20, and 24, right? Otherwise, if we did 3 times 2 times 4, we also get 24 outcomes. Okay, 24 different outcomes we can have. All right, below, it says your choices now include a Toyota and a tan vehicle. And now you can figure out the number, and you can use the fundamental counting principle to figure out that as well. Example 4, it says using the fundamental counting principle. It says the access code for car security system consists of 4 digits. Each digit can be any number from 0 to 9. Okay, so if you think about it, from 0 to 9, that's 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 options, right? So the first digit can be 10. The second digit can be 10. The third digit could be 10, or the fourth digit could be 10. So how many different it says each digit can be used only once and not repeated. Each digit can be repeated, and each digit could be repeated, but the first cannot be a 0, 1. So we're going to look at different events, okay? So I guess I kind of jumped the gun on this guy. Okay, so the first one, it says each digit can be used only once and not repeated. So then I could have 10 numbers in the first digit. I could have 9 different, because let's say it was 0 the first time. So now I have 9 different options. Now let's say it took the 1 away. Now I have 8 different options. And then now I have 7, right? And so we'd say 10, 9, 8, 7. And then when I multiply that, okay, let's multiply that. So I'm going to my scientific calculator here, and I would do, let's see, 10 times 9 times 8 times 7. That'd be 5,040. So for the first one, option A, there are 5,040 different possible codes. Okay? Now I'm just going to erase these out of here because this is actually a nice little visual. Okay, for the next one, it says each digit can be repeated. So that would be 10 for the first time, 10 for the second, 10 for the third, or 10 for the fourth, right? And so then if I wanted to figure out how many that is, I would just do, all right, 10 times 10 times 10 times 10. And I see that that's 10,000. So I go on here and I say that that would be 10,000. So notice And it makes sense. But if you have more digits in there, you would have more access codes, right? If you could repeat them. Now the last one, okay? So option 3, it says each digit can be repeated, but the first cannot be a 0 or a 1. Okay, there might be a reason for that, but let's just say, okay, so if I take 0 and 1 away from the first digit, that leaves me with 8. Now I can use any other digit except for 0 and 1 for the second one, so that leaves me with 8. And then finally the last one, now I can pick any of my 10 and any of my 10. So I figure out how many different I can have. And so I go to Desmos, and I do 8 for the first, right? 8 for the first, 8 for the second, 10 for the third, 10 for the fourth, 6,400. So there would be 6,400 or 6,400 different outcomes in part C. Okay? All right, I'd like you to try this one on your own now. All right? Now, we're going to talk about classical or theoretical probability next. And that is when each outcome of a sample space is equally likely to occur. Like there's nothing that is supposed to happen more or less than another one. So how do we find probability? Well, what we do is we take the total number of outcomes in our event that we're looking for, divided by the total number of outcomes in the whole sample space. So if I look at number 1, event A. So here's our first event. It's rolling a 3, right? So here are all the possible outcomes in rolling a 6-sided die. You can either get a 1, a 2, a 3, a 4, a 5, or a 6, right? So what's the probability of getting a 3? Well, 3 is one number out of 6. And so I'll just write it like that, 1 out of 6. That was pretty easy. Now, the next one, okay, right? Now the next one, it says, what's the probability of rolling a 7? Well, I look at my sample space, and there is no 7. So the probability of rolling a 7 is 0. It's not going to happen, right? I guess that kind of looks like an 8. But 0, that's not going to happen. All right? And finally, event C is rolling a number less than 5. Okay, so I'm going to look in here, and I say, okay, well, all the numbers less than 5, well, 4 is less than 5. So is 3, 2, and 1. So that would be 4 out of 6, which we can reduce by dividing both by 2, would be 2/3. So now you can see our probability. So here, right here, this is something that is really good to have in your notes. Okay, that would be all the possible playing cards that you have, all 52 of them right there. All right, so use this to answer example 5 on your own. Good luck, and we'll see you tomorrow.